Welcome back to CST432. Today, our topic is Decisions, Part 1. Some of the things we will look into today, first of all, will be on behavior-based robotics concepts, which is dealing with suppression and inhibition. Secondly, we will look into what are data structures and pointers, and how they will affect the way we manipulate memory and also deal with matching up patterns in your data. Finally, we will apply these concepts into the use of lookup tables for solving various problems in the robotic software. First of all, we look into what is suppression and inhibition. In behavior-based robotics, inputs that are coming into the behavior for evaluation can be suppressed using a suppressor node. This prevents the input from being seen by the behavior. In addition, outputs from the behavior, such as actuator values that be used for programming the controllers, may be inhibited by another behavior using an inhibition node. Previously, when we were studying the arbiter, we studied a fixed priority arbiter. What this means is that higher priority behaviors will overcome or replace lower priority behavior outputs. We can represent this using the suppression and inhibition representation. What we can do is that using the suppressor nodes, we can suppress the output of lower level behaviors using the upper level behaviors, and this results in a fixed priority suppression based arbiter that performs in the same way as the arbiter we studied previously. Now, it should be noted that inhibition and suppression nodes can be placed whether on the inputs or the outputs of the behaviors. So in this representation, the suppression is placed on the outputs of lower level behaviors. Now this results in the same output as what we would have received from the previous arbiter that we studied. Now we shall turn our attention to how we represent information or data storage in memory. First of all, we look into how to access memory in one-dimensional arrays. We have seen the use of one-dimensional arrays previously when we were using it for displaying strings and other related output, as well as the array used for storing the light readings in the for min-max calculation. Now, when we look at the one-dimensional arrays, we see that it is arranged in order, in sequence, in memory, usually from low memory to high memory, and each array item has a fixed size with a corresponding index. In our case, we will start the index number from 0 and increasing until the maximum number used for indexing the array. Now, when we are accessing array items in memory in assembly language, we need to take into account the size of the item, because when we are accessing memory, we need to use the address of the given location in memory to access a particular item, and this is given by the formula item address is equal to the array start address added to the value of the index multiplied by the size of the operand. If it's byte size operands, then the size is 1, since each array address would refer to a byte. If the size of the operand is 2, it means that we are looking at the half word size item, or 4 if we are looking at a word size item, which is 32 bits. This is important because if we do not get the array address correct, the item address correct, we would be referencing an invalid item in the data structure. In the previous lecture, we looked at how we can represent the actuator outputs in various variables. Now we will study how we can put them together into a collection, or otherwise known as a structure. A structure is the typical method used in the C language for grouping related items together. And in this structure, we have defined the speed and the brake values for each of the motors that we will be controlling, as well as the speaker output variables related to the tone, frequency, and the duration of the tone. Now, putting it all together into a structure allows us to reference this as a single item in an array of multiple structures, because we will use this later to represent the output of each behavior as a particular structure item in an array of behavior outputs. Let's look at how much memory one of these structures take. First of all, we have the various variables, bite-sized variables used for storing the speed and brake information for each motor, as well as 1 byte used to store the current state of the robot's movement. Now this takes up 7 bytes total. Now the next item in our array on the structure is the tone frequency and tone duration variables. These two variables are word size variables, and for the ARM microprocessor they need to be word aligned on the address that they are starting from. What this means is that the address must be divisible by 4, and in order to achieve this, we will need to add 1 padding byte before the start of the tone frequency variable, so that the alignment is kept. So in total, we will need to add the extra padding byte to the total storage requirement of the structure, which results in a total of 16 bytes for the structure in memory. So how do we access a given element in one of these structures? First of all, we note that previously we had studied how we can access a given item in an array, and that is dependent on the size of the operand. In this case, for a structure, the size of the operand is 16 bytes. So we can find out the starting address of an item by multiplying the index number with the operand size, which is 16, to give us the offset into the array start address. Now after that, given the starting address of the item, we would then add to it the offset of the given element. For example, the speed B element is in offset 2, which is the third byte in the structure. This will give us the ability to access the specific element in a given structure one at a time. When we look at the detailed memory map of this structure, we notice that offset 7 is used for the padding byte. This allows us to start the tone frequency variable from offset 8, which is divisible by 4, otherwise known as word aligned. Now there are cases where we do not want to insert the padding into our data structure. In C, we can eliminate the padding using the attribute bracket packed directive through the C preprocessor. However, this is not recommended because when we are dealing with access to memory, we need to make sure that the memory access is word aligned. But if we are dealing with network headers or other structures that are used to exchange information with other systems, it may be necessary to do so. The drawback of doing so is that we must therefore access non-aligned multi-byte values using a byte-by-byte access instead of a word access, because otherwise this will cause a misaligned data access exception on most ARM processors if we try to access a word size variable from a non-aligned memory address. In assembly language, we do not have the feature to detail out the structure of contents of a structure directly. Instead, we need to implement the structure as a separate declaration of each element in the structure. In order to ensure that the structure starts at the properly aligned address, we use the .align directive to inform the assembler that we need to start this on a word boundary. So at the beginning of this structure, we will use the .align to declare that the structure starts on a word boundary, and subsequently, after we declared various byte-sized items, and we need to align the tone frequency and tone duration items, we will also use the .align directive again to make sure that padding is inserted where necessary to ensure that the tone frequency and tone duration variables are word aligned. Okay, so once we have declared all these variables in the array, we can use the assembler to calculate out the various element offsets for accessing it in the data structure later. The element offsets are calculated using the current address of the particular item and subtract from it the start address of the array declaration. So here the dot indicates the current address of the in the assembler file, and if you want to find the offset of a particular element, we will use the label for the element and subtract from it the start of the item declaration. So after we have defined all these offsets, we will then declare the other items needed to support the mover robots that we are studying in this module. First one is the previous actuator state, which is the similar size structure to the actuator state structure, as well as a behavior actuations, which is an array of the output of the various behaviors, which consists of an actuator state item each. We can extend this to two-dimensional structures and arrays as well. In such a case, we need to take into consideration the language that we are interfacing with or we are programming for. There are two ways of representing two-dimensional array items in memory. We have to map it from a two-dimensional representation to a linear representation. Now, in the C language, the representation used is called row major linearization sequence, which means that we start from the beginning, the top row, and we move for every column item in the row in sequence until we reach the end of that row, and then we start with the second row and put it into memory. This is used in the languages as C. Now, in contrast, Fortran uses a column major linearization sequence, which means that each item in a column is put into memory in sequence, and at the end of the column we'll start with the next column, and so on. So once we know the linearization sequence, then we can then convert it into a formula for the specific address for a given item by using the formula given on this slide. First of all, we need to know the number of items per row or per column, and we will need to calculate the row address as well as the column address in order to get the given item address. One application of array manipulation is for initializing and copying memory. This is often used at the start of a program because we need to configure the memory for a given set of values. The default value probably is 0 for initialized data. And we need to copy memory from one location to another, especially when we are dealing with data structures which contain multiple items stored in a sequence of bytes. So we can consider memory as an address space consisting of a linear one-dimensional array of bytes. Now, in order to initialize this memory, we would then set each item in the one-dimensional array to a specified value. An example of this type of application or function is memset in C. If you want to copy memory, what happens is that we will duplicate the contents and the source one-dimensional array to the destination one-dimensional array, and an equivalent example of this feature in C is memmove. Memcopy is not safe for copying overlapping blocks, and we will not consider that at this point. In order to initialize memory using memset, we need three parameters. First is the address of the array of bytes that we want to initialize. Second is the value that we want to initialize it to. And thirdly, the number of bytes that we will modify. And all these are passed in parameters in registers R0, R1, and R2 based on the AAPCS convention that we studied previously. We can implement memset using two ways. One is that we will iterate through the array of bytes, byte by byte. Now, this is reliable but slow. In this example given here, we assume that the size of the number of bytes to be initialized is divisible by 4, and instead of doing it byte by byte, we'll do it 4 bytes at a time, meaning 32 bits at a time. So in this routine, what happens is that we will take the input value given to us in R1, and then we will replicate it into the other bytes in the register R1 so that the entire 32 bits is filled up with 4 of these 8-bit values. And subsequent to that, we will store this word by word into memory. Again, we assume that the memory address is word aligned so that we can perform this safely. Now we look at the copying or transferring of values from one section of memory into another section of memory. We need to consider 3 different cases. The first case is where the source and destination blocks are non-overlapping. In this case, it's pretty straightforward. The second case is when the destination block overlaps the end of the source block. In such a case, it is important that we start copying from the end of the source block to the end of the destination block and move towards the beginning. Otherwise, what happens is if we start copying from the beginning of the source block to the beginning of the destination block, the end of the source block will be overwritten and corrupted by this process. Now in the last case, we have the destination block overlapping the beginning of the source block. In such a case, we will copy from the beginning of the source block to the end of the source block into the destination block. Doing it the opposite way again will corrupt the values that we copied. So given these three cases, it is important that when we start the copying process, we check and see which situation we have in our source and destination block addresses, whether they overlap or do not overlap, and perform the appropriate action. First, we look at the memmove pseudocode. When we enter into the routine, we will check whether the destination begin address falls between the source begin and source end address. If it does, then we need to start copying from the end to the beginning, and we set a increment value to decrement. Otherwise, we will do the opposite, and this applies also for the case where there's non-overlapping, because for non-overlapping cases, it doesn't matter whether we copy from the beginning to the end or the end to the beginning. So we look at the assembly language version of this memmove routine. On entry, we have R0 containing the destination memory address, R1 containing the source memory address, and R2 containing the number of bytes to copy. First, on entry to the routine, we will calculate the source end address and also to compare the destination begin address against the limits for the source begin and source end to determine whether we need to do copying from beginning to end or end to beginning. So if we detect that we need to copy from the end to the beginning, we will set R3 to have a negative increment so that we will know that it is modifying the address pointers by decrementing them. Otherwise, we will set R3 to a positive increment. So in the actual memmove loop, what we will do is that we will read the values from the source block byte by byte and store it byte by byte into the destination block. We will use the auto increment or auto addition of the base pointer to update the address pointers. Now, since we use R3 as the increment value, we can either increment or decrement depending on the value stored in R3. Next, we look into the use of pattern matching and how it is done using pointers. Now, as an example of values stored in arrays, strings are arrays of characters. In C, strings are terminated by a null character, which is a value 0. In order to locate a pattern in a string, such as a character or a sequence of character, we require us to traverse the array byte by byte. And this is achieved using pointers in C and as well as in ARM assembly, which is what we are interested in. Let's look at an example of a string traversal algorithm which is used in structure. Structure is used to detect whether a given character is present in a string. So in the C version, we will have a while loop which checks for the value of the character that is retrieved from the array of the string array, and as long as it is non-zero, we will process it. Now, this equivalent version in the ARM assembly language is that we will load the value from memory given the array pointer and then check it against the value 0. And if it is 0, we will exit the routine. If it is non-zero, we will process the character. If the character that we retrieve from memory matches the target value, then we have found a match. In such a case, we will return the address pointer to that character. And so in the assembly language version, we will compare the value that we retrieve from the array that has been stored in the register against the target value that is passed to us as a parameter. And if they are equal, then we will return the current address pointer as the return value. If it does not match, we will then increment the pointer to the next character in the array and repeat the loop. And you can see that equivalent in the assembly language instructions that we have used. Now what happens if there's no match? In such a case, we will return a value of now, which is equivalent to 0 hexadecimal in assembly language. Now we will look into the use of lookup tables in implementing algorithms and various routines in assembly language. What are lookup tables? They require the conversion of an input value into an output value using a particular algorithm. This algorithm can be arbitrarily complex. Now the only requirement is that the inputs must be discrete, and the outputs have inputs have finite ranges, meaning that we do not have a real number as an input or an output, because it will make it impossible to store the various values in the lookup table. Thirdly, they must have a one-to-one mapping from input to output. You cannot have more than one answer for a given input. And finally, we need to take into consideration the storage space requirement for this lookup table. Let's look at how we can solve a square root calculation problem for a low-end processor. In this case, we are interested in the integer square root of a number. The number is an 8-bit value, and subsequently the square root also would be an 8-bit value. Now the integer square root means that we will not be concerned about the accuracy of the output value, only an approximation. Now this is an important factor to take into consideration when we are using lookup tables. If we are using a lookup table for storing output values, the values out of necessity must be discrete and quantized. If they are not accurate enough for your purposes, then it is not a good solution. Now assume that we have a reasonable solution using an integer square root output. In this case, for every input value for 8 bits is starting from 0 up to 255, we can pre-calculate the square root of that number offline, meaning that using a calculator or even by hand if necessary in order to come up with the output value. And these values will then be stored into the array as the value for your lookup table. And in this table given on the slide here, we can see the various output values for a range of input values that is given to us. So how do we do this in assembly language? First of all, we note that the input value x is not necessary to be stored in the array. Only the output value y is needed, because the input value can be used as an index into the array. So we save a lot on the storage of the values that is used for the calculation. We see here that we have declared a byte-sized array consisting of all the possible output values, starting from the output for 0 up to the output for square root 255 into the data structure. Next, we will perform a direct lookup of the table in order to retrieve the output value. In this case, we will put the output value in R0, and using R1 as an index, which is the x value, we will perform the address calculation with R2 having the array start address pointer. So adding the index to the array start pointer will let us retrieve the byte-sized value from the memory back into the R0 as a return value for this algorithm. Now, not many problems are so nicely defined, such as integer square roots. How do we deal with continuous or many-to-one mapping, such as the case where we have possible input values ranging from a minimum to a maximum value, and for that we will have a single output value that corresponds to this input range. To do this, we can use keys or input bins. A key maps a non-contiguous value to a specific output. Example of keys may include things like characters, like in the text character input, or else various constants that are used to represent specific enumeration types. Now, input bins group inputs into ranges for many-to-one mapping between the input values and the output. Many-to-one mappings may not be suitable for certain kinds of application which require high accuracy. However, if we are able to deal with the limited accuracy of such a solution, we can use this many-to-one mapping using input bins. The range specification must be done carefully, where we have the minimum value for a given bin and the maximum value of the given bin defined. And we also must take into consideration whether it includes the limits or exclude the limits, or include only one of the limits and not the other. If this is not defined carefully, then the algorithm will not function properly, because there may be more than one matching input bin for a particular input value. We will look again into the integer square root example, but now we will have 16-bit input values. As we know, 16-bit input values have a range of 0 to 65535. Now this is too much for storing into an array, because the RAM available on the Atmel processor that we are using in the next only has 64K of memory, and this is already taken up if we use it to store the lookup table for 16-bit input values. What we will use instead is input bins, where we define the lower range and the upper range. Now we do not need to specifically store one of the ranges, because we can represent the upper range with the next minimum value in your array. So using this technique, we will reduce the storage requirements for the input bins from 2 limits down to one single limit, which is the lower limit. And we will need to store the lower limit because we no longer have a sequential index value to use. Instead, we need to search the table from the beginning and finding a valid lower limit that would match the input value. Only then we can return the correct output value that we used. So in this case, we have again another 255 possible inputs that can be used to return a value. Now we need to add an additional item into the array, which is to represent the case where it is 65536. And because we cannot store the value 65536 in a single byte, we will represent it as 0, which is a special case which will detect in our algorithm to convert it into the proper value. This allows us to terminate the algorithm because we need to have an upper bound for comparison. In our implementation of this advanced lookup table, we will use the linear search algorithm. What this means that we will start searching from the beginning of the array to the end to find a matching input range. Now, the second thing to note is that the array for storing the information for the range as well as the outputs are split. The reason for this is because the input range is 16 bits and the output value is 8 bits. If we combine them together into a structure for storage in memory, we will actually need to use an additional padding byte in order to align each item in the array into a word boundary. To avoid the wastage of this padding byte, we will split the array lookup table into 2 arrays, one for the lower bound and the other for the actual output values. So this algorithm will take an input value in R0 and find the corresponding output value and return it in R0 as well. In addition, please note that R1 is used as an array pointer. R2 and R3 are used for retrieving the minimum lower bound and the upper bound for the current row and the next row for comparison. Other registers are used as scratch registers for performing calculations. Please note that we will use register 1 for the array index. Secondly, we will use R2 and R3 as address pointers to the lower bound and upper bound values in the lookup table. And other registers will be used for scratch registers for retrieving and comparing values in the memory. At the beginning of the routine, we will first of all preserve any register that we will modify starting from R4. And then after that, we will set up the address pointers to the minimum and maximum bounds of this given item. Finally, we need to start the reference of the array from the last item to make it easy for the comparison checking later. First of all, we need to convert the index into an offset. Now we use a temporary register for doing so because the size of the item or operand in this case is 2 bytes. Unfortunately, when we want to load a 16-bit value or half word from memory, the address format for LDRH that restricts us in what we can use as the offset operand. So we need to pre-calculate the offset value and put it into a temporary register in order to load it from memory. We will also load the next item, which is the upper bound of the range that we want to compare against, into a register, as well as to check whether the value that we loaded is 0, because we will need to convert it into 65536 manually. Next, we will check whether the input value falls within the lower and upper bound ranges that we have retrieved from the array, and if it does, then we will go and process it. Now if it does not match, we will then see whether we have traversed the entire array. If not, then we will go to the beginning of the loop and try again. Now if there's no match found, we will return an error value. Otherwise, we will retrieve the address pointer for the output value y, and using the index that we have determined previously, look up the output value to be returned. That's all for part 1. We will look into how to implement some of the features in the Moore robot using these techniques in part 2 next time.